Welcome back. We're going to continue with the OLS regression in our video series. In this particular video, I'm going to take you through building a simple OLS regression model using SAS. We will have only one independent variable. So this is OLS regression with only one independent variable. And then we're going to study what the SAS output looks like. So when we do a regression, either with SAS or any other statistical tool, we get a lot of outputs. So I will go through the outputs one by one as well and explain what each terms mean, what is the interpretation, and how do we test and check whether the model is good, bad, ugly, etc. so on. So let's have a look at the syntax for PROC REG first. The PROC REG procedure runs very simply: PROC REG data equal to dataset name, which is common to all procedures. Then we have the model statement. So model statement runs model dv equal to iv1 space iv2 space iv3 all the way till ivn. So here dv is the dependent variable and iv are the independent variables that we want to build. So till now we've only covered linear regression using one variable. So I will use only one independent variable for now, and we will move on to multiple linear regression at a later lecture. So let's build a model. The model that I want to build is on the HSB2 dataset. It's going to be a simple model. I want to model, let's say, math as a function of science. So math is going to be the dependent variable, science is going to be the independent variable. So let's build a model. PROC REG data equal to the dataset name, so library.hsb2 model math equal to science, run. And that's all I need to do for now. I'll just put in an ODS HTML statement to get HTML output. I select this and I run this model, and there we have it. We have our regression output. So I'll just open the HTML fit, and so here we have our model details. Now the PROC REG procedure prints out a lot of tables, and I'm going to explain what it means. So the first table that we get is the number of observations that have been used in our dataset. So we've used all 200 observations, and then we get is the ANOVA table. So the analysis of variance, and you get an F value, which is the F test, and a P value. So it's the question that we're going to ask ourselves is, what is this ANOVA testing? So what is the null? What is the alternative? So an ANOVA, as we've covered in our previous class, essentially means that we are testing some hypothesis in the end. So the null hypothesis for ANOVA is that we are testing the first particular assumption. So if I look at OLS regression and the assumptions, the first assumption is that there has to be linear relationship between independent variables and the dependent variable. So what we are testing over here is whether the first assumption holds true or not. So the null hypothesis over here is that the independent variable has got no linear relationship with the dependent variable. The alternative is obviously that there is a linear relationship with the dependent variable. And if I look at the p-value, the p-value is low, therefore null has to go, therefore there is a linear relationship. So our first assumption is actually met, and we can proceed ahead. If this p-value is higher than alpha, and alpha is typically set at 0.05, it would essentially mean that the regression is insignificant and we cannot proceed. So if this p-value goes higher than alpha, you don't even need to look at any other table below, because the regression itself is insignificant. And how this regression is actually going to work, I'll come back to these sum of squares and the mean sum of squares a little later. Now let's move on to the next table. So here we have the root mean square error, the dependent variable, the dependent mean, coefficient of variation, R square, and adjusted R square. So let's have a look at each one of them in turn. So what does the root MSE actually imply? The root MSE stands for root mean square error term. So as we know that in regression, we are looking at the mean squared error term. So if this is my regression model, Let's start off with a fresh sheet. So if this is my regression model that I'm working with, so let's see this, and I have some of my observations. And this is the regression line of best fit over here. So for each of these observations, we fitted in we fitted in the line with the least squared error term. And if we look at the error, for each observation we have an error term. Right? And we square the error to find out to make both negative errors and positive errors with the same sign. So to ensure that all errors have a positive sign, we square the error term and then we add it up. So this is called as the sum of squared errors, or the SSE. And we identify the line which has the minimum sum of squared errors, and that is a regression line. So that part we covered in our first few lectures. Now if I take the under root of the SSE, so that becomes the root mean square error term, so that is the RMSE. So if I take the under root and divide it by the number of observations, so if I take the under root, it becomes the squared error, so it becomes we remove the sum of squared error term over here and divide it by the number of observations. So this gives us what is the average error in our model is going to be like. So I can't look at the full SSE because as the number of observations increases, the sum is also going to increase. So looking at the SSE by itself does not give me an idea of what the average error is going to look like. One way of looking at the average error is I sum all the errors up. So summation of the error term and divided by n. Now the problem here is that we've already know that if I sum up the error term, it will come out to be 0 because positives and negatives are cancelling out each other. So 0 divided by n is still 0. So I get an average error of 0. So the E bar, or error average, is 0. So I can't look at the average error to figure out what is the error that this model is likely to predict. Some statisticians use the error mod. So we ignore the sign, we assume all errors are positive, add it up, and summation of error mod divided by n. However, this is not part of OLS regression. While this is used in some other kinds of regression, OLS does not use the mod. The OLS uses the sum of squared error terms. So therefore, to get it onto the same power, we have to take an under root and we divide it by the number of observations. So that gives us the root mean square error term. So take the sum of squared errors, divided by the number of observations, and then take the under root. So this is not under root of SSE divided by n. This under root actually goes all the way up. So the root of the mean squared error term. So this is the RMSE that we are talking about, and the average error over here is 7.2885. So this is looked at as a goodness of fit measure, that if I'm fitting math as a function of science, and by looking at only the science score, I'm going to predict the math score. What is the average error that I can expect? So the root mean square error term tells us what is the average error that you can expect. The dependent mean is nothing but the mean of the dependent variable. In this case, it's maths. So if I look at math in my original data set and I look at the mean, I get 52.645, and that's what the dependent mean over here also means. So the mean of math, or the mean of the dependent variable, is 52.645. Now the next goodness of fit measure that we get is the coefficient of variation. The coefficient of variation is nothing but the root mean square error divided by the dependent mean. So if I divide 7.2 by 52.64, I'll get the coefficient of variation. So it's a percentage term to understand. What it essentially means is, if let's assume that my regression lies in hundreds of thousands. So this is 100,000, this is 200,000, this is 300,000, and so on. So I get a RMSE value of, let's say, 50,000. So how good or bad is this? If I look at RMSE of 50,000, it looks pretty bad, that my error is huge. But compared to what? Right? We have to figure out, is it a big error? Is it a small error? Therefore, to get a sense of what is the average y value that we're looking at, if I identify the average for y and say this is y bar, and y bar is, let's say, 250,000, therefore an error is the coefficient of variation will become 50,000, the RMSE divided by the mean of the y or the dependent variable, 250,000. So this tells me that the error is about 25%. Sorry, it's actually, so if you look at this, so it becomes about 25, yeah, so 20%, I'm so sorry, so it becomes 20%, so 50,000 over 250,000 becomes one fifth, and that's about 20% error. So RMSE is nothing but the coefficient of variation is nothing but the root mean square divided by dependent mean, which gives an idea if what is the average error in percentage terms around the y variable or the y hat. So this gives me 13.8%. So this is a method of bringing both the root mean square error and the dependent variable onto the same scale. Then the next goodness of fit measure in this table is the R square, and this is the most popular and the most used and abused, if I may use the term, method of determining how good is our model. So whenever we build an OLS regression model, the first question any analyst or data modeler gets asked is, what is the R square? And in most cases, it is assumed higher the R square, the better the fit of the model. And I'm going to explain what does R square mean, but I'm also want to reinforce that R square is not the end all and be all of measuring how good a regression model is going to be like. Now uh, the the specific definition of R square is the percentage variance of the dependent variable explained by the independent variable, or what percentage of the variance in y-axis or in the y variable can be explained by the regression model. So let's pull up a new sheet, and I'm going to explain how R square is actually going to be calculated. And for this, we're going to look at the ANOVA table as well. So assuming that I have my data set, and let's assume this is the scatter diagram. And this is the scatter diagram. So we don't have so I've got X variable over here. Make it smaller. So we've got X variable on the X axis, we've got Y variable plotted on the Y axis, and every observation in my data set is plotted onto this two-dimensional graph. Now, if we don't have any regression model and we want to predict the value of Y without a regression model, so what is the best predictor of Y if we don't have any other information? So what will be the best predictor? In absence of any model or data point other than the y variable itself. So in this case, we're going to use a measure of central tendency. So what's the best measure of central tendency to use if I want to guess the value of y? So let's take an example that we have a class, and we've got the age of the student, and we've got the height of the student. So we've got a class, let's say 12-year-olds. Most of them are 12 to 13-year-old children, and that's the age of the students. And we've got height of the students in centimeters, so let's say 120 centimeters, 119, 135, 100 centimeters, and let's say 124 centimeters, and so on. Now you're asked to predict the height of a random student. So I pick up a student at random and I ask you to predict the height, and we don't give you any other information, so no gender information, no age information, nothing is given regarding the students. You have to predict the height. In absence of any other information, the best prediction that you can do is you can make the average height. So you can predict what is the average height and say this is my prediction. So let's say average height comes out to be 120 centimeters. So you predict that the random student that you will pick up will have a height of 120 centimeters. So in this case, the value of y bar, so let's say y bar lies somewhere over here. So this is y bar. So this becomes our default prediction in absence of any regression model or in absence of any independent variable in our model. So if y bar is my best predictor, then what is my error going to be like? So what's my error? So in this case, I will calculate the error for each observation from the y bar line. So I calculate the error like, so I calculate the error for each observation from the mean value of y. So I get positive errors, I get negative errors. So you get the point. So I calculate the error of every observation from the mean value and I square this term. So I call this the sum of squared errors. Let me just say, so sum of squared error term from the mean. So this is my baseline, or this is the base model which I can create without building any regression. So this is my base model. Now I go ahead and actually build a regression model. Right, so I go ahead and build a regression model. I have x variables. So for example, I have the age of the student as a criteria, or I have weight as a criteria. So I could have age, I could have weight. So let's assume that we have weight of the student as an independent variable, and I go ahead and I build a regression model which gives me a line like this. So now whenever I pick up a random student, I get the weight of the student as an input variable. So using the weight, now I have to predict the height. So in this case, the error term in each observation is going to be the error against this particular line. So I see now the average error is obviously going to go down a lot, because instead of guessing the mean value of y for any random student, now I have an input variable, and based on that input variable I make a guess regarding based on this line. So for example, for this student, I have to predict the height of the student. I get the weight. So for example, for this student, the weight is xi, right? So xi. So I put xi into the formula. Based on this line, xi is going to predict yi, and this is the actual height of the student, which is yi hat. So the error term is this distance. And similarly, for each of the observations, I get another error term. So this is the error of the model. So now I can calculate the sum of squared errors for the model. I have sum of squared errors for the base, which is without any model. So how good is my regression? So this is where the ANOVA comes into play. So if I look at the sum of squared errors uh, for the model, so this is the sum of squared errors for the base model, and this is the actual error model that I get. So while it's written a little in the opposite way, what we can see is 6948 is the sum of squared errors if I have to predict the mean value of y for every particular observation. And as you will see, if I'm calculating the mean error against y and squaring and adding it up, this is nothing but the variance of the model. So this is nothing but variance. The baseline model is variance of the variable y around y mean. So that's the total variance. So if I look at this another way, the sum of squared errors for base is nothing but variance in y. So that's the total variance that we have in our model. And if I look at the variance around the error, so this is the variance of the regression model. So this is variance around regression. So now if you look at the formula for, if you look at the explanation for R square, it says percentage variance of the dependent variable explained by the independent variables. So let's have a look at this again. So when I am capturing, or when I'm calculating the average error around y bar, that is nothing but the variance around the variance of the variable y. And if I'm calculating the error around the regression line, so that's the variation around the regression line itself. So now if I look at the total variance as a percentage that needs to be explained, can I take the variance of regression and divide it by the variance of the total variance in the dependent variable y? So that will give me a percentage term, or that will give me a number, and I do 1 minus the variation in regression divided by total variance in y. So if I subtract this fraction from 1, this will actually give me the R square, or this will give me a term which says what is the total variance in y which can be explained by this model. So uh, variance or the R square is nothing but the total variance in the dependent variable. So we've already covered standard deviation and variance in our first few lectures, and the standard deviation of variance is nothing but the difference between each observation and its mean, and that's what we've shown over here. So that's the total variance in my dependent variable, which is in the denominator over here. In the numerator, I put in the total variance in my error term from the regression line, which is nothing but the sum of squared error of the regression. If I divide the sum of squared error of the regression over the total variance, so that gives me a percentage term of how much is the explanation done. So I do a 1 minus to get the opposite side, and that gives me the total variance which has been explained away, right? So the biggest error that I can make, so another way of looking at it is the biggest error that I can make in my model prediction is the variance of y, because I can't go worse than this. If I have no model, I simply predict the mean of the variable y for every case. So it doesn't matter what is the age or weight of the student. My prediction in every case is going to be the height of the variable, the average height. So whatever is the student for which I have to predict the height, it always comes out to be the mean. So if I make a mean prediction for any way student, the error in my model is going to be the variance of y itself. However, now with a regression model, I have fitted in a line between x and y. Now, depending on the value of x, I'm able to predict or I'm able to make an educated guess regarding the value of y. So my error actually goes down to variance in the regression model, and that is the variance of my residual or the error term. So from now, a maximum error was 100%, which was the variance in y. Now I'm making an error which is, let's say, not 100%. I'll just call it var y. This is my total error, and this is the maximum possible error in my model. This is the error I'm currently getting, right? So if I do 1 minus variance in my regression model divided by my variance over x, variance of my dependent variable, sorry, so this will give me the total variance that I have been able to explain away. So this was the maximum possible error that I could get, but I'm only getting this error now. Therefore, the total error term which has been explained away is 1 minus variation of the regression divided by the total variance in my dependent variable. So if I look over, so if we look at the output in the ANOVA table, we actually get three sum of square error terms. So one is the model sum of square errors, the other is the second is the error sum of square errors, and then we have the total sum of square errors. So I'm going to explain what each of these mean. Let's go back to our graph over here. So I've tried to explain what does R square mean and how we talk about explained variance versus unexplained variance. So let's build a new sheet again, and I'm going to fit in those three error terms over there. So I have my data set plotted as a scatter diagram. Let's build a scatter diagram. And there we have a scatter diagram. And I know that for if I don't have a regression model, my best line of fit or the best prediction is always going to be y bar. So let this be the y bar line. So this is the value of y bar, and this is my regression model which I fit, and this is the line of least error. Let's put in a few points here as well to make it fine. So this is the line of least errors. Now let's pick up one particular point over here, and let's say this is the observation which we are talking about, and this is the observation at point xi. For this particular xi, the predicted y hat lies over here. So this is y hat, and the actual value of yi lies over here. So this is yi. So if I look at this distance, so this is the residual, and if I sum it up, this will be the error sum of squares. And if I wanted to predict the value of this particular observation or any random observation without any without any input, the my best guess would have been y bar. So this is the original error. This is the maximum error which I can have in my observation. So this is the total variance in my model, or variance of y. So what I need to do is I need to build a model which is going to explain this variance. So this is my total variance, right? This is the variance, or this is the distance from the mean and the actual predicted value. So this is the model variance that we have, and this is the error term. So the total variance that I need to explain for this particular observation, variance of y, which is the distance from y bar and yi, is going to be the model variance, which is the variance between y bar and y hat. So I'll call this as the model variance plus the error variance. So that's the total variance which I can explain. So in this particular case, if I look at the data or the table, what it has done is it has given me the total sum of squared errors for model, total sum of squared errors for error, and the total. So over here we know that the total variance in my data set is 17466. So this is the total variance, or in fact this is only the variance of the y variable, or the dependent variable. So the total variance, when I add up this, not only for this observation but for every observation, the total variance of y is 17466. The total model error, so model error is or the model variance is my variance between y bar and each of the predicted values as per the line. So this is the variance which I am getting, which is 6948, plus the error, which is the unexplained term, is 10517. So this, if you add it up, it will come exactly the same. So the R square is the variation explained by the model as a function of the variance of the total model. So if I take 6948 and divided by 17466, so this will give me the R square of the model. Or the other way is that, since I know 6948 plus 10517 is the same thing, so I can take is 1 minus 6948 divided by 6948 plus 10517, which is the total variance in the model that needs to be explained. So this is the variance explained by the model, plus this is the variance of the error term left over, and the total variance explained by the model alone. So this gives me the R square. So the R square formula remains the same. I can either explain it as the total variance in my dependent variable, which is the denominator, and the variance which has been explained by the model from the mean. Right? So this is the variance which has been explained. This is the total variance that needs to be explained, and R square is simply the ratio. So therefore we call R square as the total variance which has been explained by the model in my dependent variable if I use the independent variable. So this is what an R square looks like. And if I copy this table out, the Nova table out into an Excel sheet, let's copy it over here, right? And let's try and figure out what the R square is going to be like. So I know model as explained is the 6948, and the total explanation that needs to be done is 17466. So this gives me 40%, 39% has been explained. And if I compare it with the R square which has been published in this data set, so there is the R square, and we get it's exactly the same, and 39.782%. So in SAS we only get up to 4 digits. So let's bring it down, and there we have it. So the R square is nothing but the sum of squared errors, or the sum of variance explained by the model divided by the total variance in the model. And the variance we are talking about is variance from the dependent variable mean. And the summation of these two, the error variance and the model variance, will always be equal to the total sum of our corrected, or the total variance in our dependent variable 17466. So there's a rounding off error over here when we are converting it from SAS to Excel, and that's what R square essentially means. So this table gives us the total variance from the regression in an ANOVA format. So this is our goodness of fit table. It tells us various measures by which we can measure the goodness of fit of the model. The most, as I explained, used or abused is the R square. It quickly tells us what percentage of the variation can be explained. In a perfect model where there are no errors, the R square will be 1. If there is no linear relationship between dependent and independent variable, and the model is not able to explain any of the variance, then our best bet or best guess regarding the dependent variable will always be the dependent variable mean. In that case, the R square will approach 0. So the R square is a value which will range from no variance explained to all the variance explained, and denominator is total variance in the dependent variable itself. Therefore, the R square ranges from 0 to 1. The root mean square error, as I've explained, is simply the square root of the summation of the squared residual term. The coefficient of variation is nothing but root mean squared divided by the dependent mean, and that was the goodness of fit table. So let's move on to the third and the most important table, which is the parameter estimates. So if let's look at these parameter estimates. The parameter estimate is nothing but my model, and if we recall the model, let me make some space. So model is simply that y hat is equal to beta naught plus beta 1 x, where y hat is the predicted value of y given x, and y hat is not the actual y. Y, if we want to, y is simply y hat plus the error term. So y hat is the predicted value of y given x, so and beta naught and beta 1. So this is my intercept term, and beta 1 is my slope against the variable x. So let's have a look. So intercept or the beta naught is 21.709 and slope is 0.59. So what it essentially is telling me is, so let's make some space again. Let me put in the eraser function. Yeah, let's get back to ink. So what it essentially telling me is that math has a function of science. So math is equal to 21.70 plus 0.59, 0.59 into the science score of the student, and that's my model. So math, which is my dependent variable y or y hat, is simply beta naught plus beta 1 times x. So beta naught is 21.7, beta 1 is 0.59, and x is my independent variable, which is science, and that's my regression model that we've built. And we also have a very interesting column over here, which is known as the standard error of our estimate. So standard error is what is the variance in the error in the estimate that we can generate. So we know that based on the formula for intercept and for beta naught. So if we look at the formula for beta naught and beta 1, right? So these are the estimates for these are the formula for beta 1, which is xi minus x bar into yi minus y bar and so on. So here we are using the mean of x and y, and over here these means refer to the population mean and not the sample mean. But since we are using sample means over here, there is a possibility of sample being different from the population mean. So we have a confidence interval around that. So when we are estimating the population mean using only the sample means, we always have a term called the standard error of the mean, which we've already covered in the previous lecture. So there is variation around our estimate regarding the population mean, and if I use that standard variance into our beta 1 estimate as well, therefore that standard error will get propagated into our intercept estimate as well. So this parameter estimate is our estimate regarding the population using the sample that we have, and the standard error of this estimate is 2.75. Now in the next column we get is the t value and p value. So therefore a probability, or sorry, an hypothesis test has been carried out. So this is an example where a single sample t-test has been carried out. The null hypothesis over here is that the estimates, both intercept and the beta 1 estimates, are actually 0. So if one sample t-test is carried out, the h naught over here, so let me carry out a new sheet. The h naught here is that estimate of population is equal to 0, and HA is that estimate is not equal to 0. So i.e. the H naught is that there is no linear relationship between science and math. Alternative, that there is a linear relationship. So if I look at the t-test. So we know that t-test for one sample is x bar minus uh, sorry the estimate, so the h naught value minus the sample value divided by the standard error, or it can be, sorry, it is actually the sample mean minus the h naught, or the hypothesized mean divided by the standard error. So in this case, the sample mean that we are getting for beta naught is 21.7, so it becomes 21.7. The hypothesized mean is that this 21.7 is actually population mean of 0, so this becomes 0 divided by the standard error. The standard error in this case is 2.75, so the t value essentially becomes 21.7 divided by 2.75, and if we look at it, the t value comes out to be 7.88, so this is exactly equal to 7.88. Now if I doing this at alpha equal to 5%, I know the critical value lies at plus minus 1.96. So is this t value in the acceptance region or the rejection region? So if I look at the t distribution once more, and this is the t distribution, t equal to 0, so the acceptance region for the null lies from minus 1.96 into plus 1.96, and I see that my t value 7.88 lies somewhere over here, so it lies way outside into the rejection region. So therefore we reject the null hypothesis. The null hypothesis rejected, the estimate of the population is not 0, and we go with the alternative hypothesis, the estimate is 0. So essentially what we are doing is we are checking if this estimate using the sample is significant or not. And in this case, the p-value is less than alpha, we say it is significant. The same thing we are testing with the parameter estimate. So the way t-value is calculated is simply the estimate divided by the standard error, because the null is that this estimate is actually 0. And this p-value also comes out to be less than alpha. Therefore, this variable has a significant relationship with the dependent variable. In case this p-value is greater than alpha, what it essentially means is the parameter estimate that we are getting is insignificant, therefore it should not be in my model. And if that's the only variable, and if this p-value is coming out insignificant, therefore no linear relationship exists, and even this p-value will come out to be insignificant in that case. So this is what a PROC REG output looks like. And one way we can actually go about implementing this is, I'm going to implement this model onto an Excel as well. So let's have a look. So this is my Excel model. I want to match destination formatting here, and let's pick out math and science actually from here. So this is math and science, and I will create a variable math predicted. So math predicted is going to be the intercept, so let's use the locking formation, plus 0.59, again lock it, into the value of science for that student, and there we get the predicted math score. Predicted is 43, actual is 44, not bad. And let's have a look. So this is my prediction math predicted scores for math. So this is my y hat, this is my actual y. Let's have a look at the residuals. I know based on the assumptions of OLS regression, these residuals need to be 0. The total residual needs to be 0. So let's do predicted y hat minus y and do it, calculate for all the way. Let's take out sum of the residuals, and if it's not 0, then we've done something wrong. As you can see, 0.0, so you have some rounding off error, but that's because we're copying it into Excel and running it. So essentially the mean residual is coming out to be 0, and that's what one of our assumptions of OLS tell us, that if I look at the assumptions, the mean error or the residual has to be 0, and this this residual has to be normally distributed around 0 as well. So we'll do a normality check later on when we use it using statistical tools, but on Excel we're going to let it be. So this is my mean residue. Now what happens if I take the correlation between the predicted and actual? So I look at the correlation between predicted and actual. So this is my R. Something wrong with the formula, let's check it out. So let's look at R, which is the correlation between the actual and predicted. So it comes out to be 0.63. It's highly correlated. And if I do the R square, is this R square the same as the one which we calculated? It's come out to be the same. So if I look at on the SAS output, the R square is 0.3978, and the square of the correlation between the y hat and y variable is also 0.3978. So that is another interpretation. R square is nothing but the square of the correlation, or how strong is the correlation between the predicted and the actual variable. So that's another interpretation of R square. Now R can be positive or negative, but R square is always positive. So R square, R or a correlation can range from -1 to +1. If for R square can only be positive, so if I square of -1 is still 1 and the square of 1 is also 1, the minimum R can be 0, so the square of 0 will also be 0. So R square can range only from 0 to 1. So R can range from -1 to +1. R can only R can range from -1 to +1. R square can only range from 0 to 1. So we've already concluded that R square can be interpreted as the total variance in the dependent variable as explained by the model. The other interpretation is the strength of the linear relationship between the predicted value of the variable and the actual value of the variable. So that's another way of looking at it. Now